Hello everyone, this video is brought to you by the Atılım Üniversitesi OpenCourseWare project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 11. A small mass m slides from rest down a smooth slope, dropping a distance h in elevation. It strikes the end of a rod of length d and mass M and sticks to it. The rod is initially at rest and fastened by a pivot p. In terms of the given quantities, what is the speed V of the free end of the rod just after the collision? The rotational inertia of the rod about its center of mass is 1/12 times M times d squared. Okay, we are only given the rotational inertia of the rod about its center of mass as 1/12 times M times d squared. The speed of mass m just before the collision is found from an application of mechanical energy conservation. That is, m times g times h, which is the initial energy, equals 1/2 times m times v squared, which is the final energy of mass m just before the collision. Then the speed of mass m, v, is obtained as square root of 2 times g times h. The rotational inertia of the rod about point P is obtained from the parallel axis theorem. That is, I rod equals I com plus M times x squared, where x is the perpendicular distance from the center of mass of the rod to point P. And we write the given expressions into the corresponding places to get 1/12 times M times d squared plus M times d over 2 squared. Therefore, the rotational inertia of the rod about point P is 1/3 times M times d squared. With this, the rotational inertia of the rod plus mass system is found as I system equals 1/3 times M times d squared plus small m times d squared, or 1/3 times M plus small m times d squared. Next, the net torque on the system is 0. Then, angular momentum is conserved. That is, Li equals Lf. Angular momentum of the rod before the collision is L rod I equals R times P times sine theta. That is, M times R times V times sine theta. And because rod is initially at rest, that is, V rod equals 0, then L rod I equals 0. And the initial angular momentum of small m equals R times P times sine theta, or M times R times V times sine theta. From the figure, it is easy to see that angle theta is 90 degrees. Therefore, Lmi equals m times d times v. As a result, the initial angular momentum of the system is due only to small m, that is, Li equals Lmi equals m times d times v. Next, we use a definition of angular momentum for the angular momentum after the collision, that is, Lf equals I system times omega. Now, if we use the relationship between the linear speed and the angular speed for the V, that is, V equals omega times d, then we obtain the angular speed as V over d. Now, by the conservation of angular momentum, that is Li equals Lf, we have m times d times v, which is equal to 1 over 3 times capital M plus small m times d squared times capital V over d. After some cancellations, we obtain m times small v equals 1 over 3 times capital M plus small m times capital V. Here it is convenient to use the expression that we have found for small v, that is 3m times square root of 2 times g times h equals capital M plus 3m times capital V. As a result, the speed capital V of the free end of the rod just after the collision is obtained as 3 times small m times square root of 2 times g times h over capital M plus 3 small m. Okay, this is the end of the discussion of this problem. Thank you for your attention and see you in the next video.